Let us move into the next type, stereoselectivity. What is a stereoselective reaction? It is a reaction in which there is a choice of pathway, but the product stereoisomer is formed due to its reaction pathway being more favorable than the others available. The reaction is highly controlled by the most stable transition state. If more than one reaction could occur between a set of reactants under the same conditions, giving products that are stereoisomer, and if one of the product is formed in greater amount than the other, the overall reaction is said to be stereoselective. Let us take this hypothetical example. Suppose there are two reactions that could occur between the hypothetical reactant A and B under the same conditions, giving stereoisomeric products C and D. There can be two possibilities. The two products formed in equal amounts, that is 50% of each isomer. The relative yield of each product is 50%, and the overall reaction between A and B is not stereoselective. Let us take our next possibility. Suppose two reactions could occur between the hypothetical reactant A and B under the same conditions, giving stereoisomeric products C and D, where the relative yields are 75% and 25%. The overall reaction between A and B is said to be stereoselective because the reaction pathway has decided which one of these isomeric products should be formed in greater yield. Let us take another example, the cycloalkene. On hydrogenation using palladium catalyst, 2 is found to be the major product. Thus, the overall reaction between 1 and hydrogen is stereoselective towards the formation of 2. The term stereospecific is sometimes used to mean 100% stereoselective. However, the original definition of the term stereospecific is different. So, it is best to avoid using the term stereospecific to mean 100% stereoselective. All stereospecific reactions are stereoselective, but not all stereoselective reactions are stereospecific. Please keep that in mind. Let us look into another example. When an alkene undergoes addition, two new sigma bonds are formed. If we think of an alkene having two phases, say top phase and bottom phase, then the two new sigma bonds can either both form on the same phase, which we call it as syn addition, or they can be formed on different phases, which we call anti-addition. Syn addition results when the two new bonds are both formed to the same phase of the alkene. In this case, they are shown to have formed on the top phase. Anti-addition results when the two new bonds are formed to the opposite phase. In case of simple alkene like ethene, the free rotation of the carbon-carbon bond means that the two product structures are conformational isomers and they can rapidly interconvert. However, in the case of cyclic alkenes, where the ring structure prevents the free rotation of the carbon-carbon sigma bond, the two products are stereoisomers and they are not conformational isomers, and they are more obvious. Another point of view. The addition of molecular bromine to cyclohexene is stereoselective because only trans dibromide is produced. Let us take another example. A reaction in which only one stereoisomer among a mixture of stereoisomer reacts can also be considered as a stereoselective reaction. A reaction that can in principle produce two or more isomers but in fact produces only one stereoisomeric product can also be considered as a stereoselective reaction. So in this case, the cis isomer undergoes a reaction giving rise to a product, whereas the trans isomer does not undergo the reaction. Selectivity is not only a quality but also a common sense, says Hemant Gangwar. So the reactions use this common sense through their stable transition state. They get the information from their stable transition state and they select the products formed. Thank you for watching.